So here it is again at the top of the next slide with a little table that just summarizes some of the conventions here. So if we're talking about delta S of the universe, right, the second law tells us that for a spontaneous reaction, delta S is a positive number. But as you've seen, and through this derivation now, right, if delta S is always positive of the universe, so here it is, if that number is positive, well, if delta G of the system is equal to negative T, delta S of the universe, that means that this must be negative, always. And it just comes from how we derived it. That's why delta G is negative for a spontaneous reaction. And obviously, the opposite will be true, so I don't need to really talk about that. If it's non-spontaneous, then delta S is negative and delta G is positive. Okay? And all of that's kind of summarized right here. It's just, now these are just logic statements. But now we get to the last statement here. But what happens if it's neither? What happens if, things don't seem to be changing? They've reached a nice stable equilibrium, that dynamic equilibrium, which we have a whole chapter coming up on equilibrium. Okay? When the system is at equilibrium, look what happens. Delta G of the system is 0, as well as delta S of the universe. The entropy is not increasing or decreasing, and delta G is 0 when you're at equilibrium. Now, what does that mean? What does that mean? We talked about the car engine, right? You got a reaction happening in the engine. It's throwing off a whole bunch of heat, right? So that thermal energy in the car, right? If I take delta G equals delta H minus T delta S, and let's just talk about that thermal energy that you're producing in the car engine. So I'm going to rearrange this. Delta H is equal to delta G plus T delta S. Okay? Well, delta G, the Gibbs function, this is the useful energy that we can get some work out of. It can be used for work. Whereas this is still energy, okay? But that's the energy of dispersion that can't be used for useful work. This is just dispersed. It's not available for useful work. So in the car as an example, the useful work is to propel the car. And the rest of that heat energy just dissipates off as, that's too hot to touch. Let's put it in another context here. Maybe this one will make more sense. Let's look at two containers of water that are connected at the bottom. Let's put a little gate in the middle of them. And if we start here, what do you suppose is going to happen to the water level if I remove that gate? What's going to happen?
Balance out.
It's going to equalize, right? The levels of the water are going to be the same, right? It's going to turn into this. But what happened to get there, right? This water is moving in this direction. Right? If we put a little water wheel here in the middle of it, we can get some useful work out of that. But once things have stabilized and the levels are the same, there's no more flow of water, we can't get any more work out of that. Delta G is 0. We're at equilibrium. Delta G is 0. No useful work. Whereas here, we could actually make a delta G argument from the starting conditions. You see where we're going there? There's another way I want you to be thinking about this too. I use a diagram like this a lot, especially when we get to later and later chapters. If we draw a graph like this, where we'll have delta G on the x-axis, and on the y-axis, and on the x-axis we have something called the reaction coordinate. What that means is on the left-hand side we have all reactants, and on the right-hand side we have all products. And we can actually draw a graph for a fictitious reaction that starts with reactants and goes to products. And if we follow the delta G on that, maybe it will look like this. Whereas if we're starting the reaction with all reactants, and we know then that if we let it go, just kind of like a ball rolling down the hill, this is going to proceed in the forward direction towards products, towards making products. Now, most of the reactions you've seen in Gen Chem go to completion. If it went to completion, then it wouldn't be a curve like this, it would be a ramp that goes all the way down to completion. But when we start looking at reactions that don't go to completion, instead they go to equilibrium when both products and reactants are present when the reaction's done and nothing else is happening. So we could have then started the reaction, say, with all products, and it's going to proceed in the reverse direction. But at some point when it hits equilibrium, that's going to be when the ball stops moving, when we're down at the bottom of this curve. This is going to be at equilibrium, and we're at equilibrium, the change in free energy is equal to 0 because the ball isn't moving anymore. Okay? It's the change. You get the energy by delta G moving from one state to another state. But if you're at equilibrium, the states aren't moving anymore. Delta G is 0. No useful energy. Okay, so let's get into this slide here a little bit. This actually summarizes a lot of the work that we did early on when we're looking at our master equation here. We looked at all 4 of these conditions where, up on top, the first line where we have delta H is a negative value and delta S is a positive value, and then we can see ultimately what's going to happen there with delta G, right? Remember doing this exercise? So that's now summarizing what we've been learning about. It's always spontaneous. And the reverse, right? If you have a reaction that's endothermic, it's positive for delta H, and you can tell that the entropy is always going to be decreasing, then it will never be spontaneous. But then as we discovered, like this one and this one, where whether it's spontaneous or not depends on the temperature. At high temperatures, it'll be one way, and at lower temperatures, it'll be another way. And we talked a little bit about that with respect to ice going to water. We know, and we did this discussion, we know that at 25 degrees Celsius, that reaction is spontaneous, right? And at some temperature, lower temperature, let's say minus 10 degrees, it's non-spontaneous, right? Remember that discussion? So that's a perfect example. We can actually calculate what temperature does it change from being spontaneous to non-spontaneous. That's all built into this equation. Delta G is equal to delta H minus T delta S. Where it changes from going from spontaneous to non-spontaneous, or vice versa, is going to be at equilibrium. At equilibrium, delta G equals 0, as I've just been telling you. So if this is 0, then what do we have? We have delta H is equal to T delta S, and the temperature at that equilibrium is equal to delta H minus delta S, divided by delta S. You'll see what I did? Nothing up my sleeve. So this is the temperature at equilibrium. At equilibrium, delta G equals 0. And that's the equilibrium where the solid ice is transitioning to the liquid and back and forth. They're both present at that transition. And who remembers what the temperature is for this equilibrium? It's 0 degrees Celsius. It's the melting point or the freezing point. That's where it changes. Above 0 degrees Celsius, we know that ice will spontaneously melt into water. And below 0 degrees Celsius, we know that that transition is non-spontaneous. If we go back to this slide, look at these numbers. I'll remind you. We calculated what the change in entropy is at that transition. It was 22 joules per mole. Okay? And I reminded you of the delta H of fusion of that. That was 6010 joules per mole. Remember all that? 6010 joules per mole divided by 22 joules per mole. What is that number?
273.
273. It better be 273 Kelvin, which is 0 degrees Celsius. Okay? And you might even notice that this relationship here, I can also rewrite it as delta S is equal to delta H divided by temperature, which looks like Clausius's original description, mathematical description of entropy. See? So it all goes round and round and round. So when delta G is 0, let's just highlight now, when delta G is 0 then, we can rearrange our equation and solve for that temperature when we're at equilibrium, when delta G is 0. That's going to be above the equilibrium. That's going to be where it's spontaneous or non-spontaneous. And below that equilibrium, it's the reverse. Okay? Because that ice to water shift happens at the melting point, at the freezing point. That's when the system's at equilibrium. Okay? This is an equilibrium reaction here. The arrow goes both ways. And then we solved it, right? We put in those values. Delta S of the system was a positive 22 joules per mole. And delta H of the system was 6,010, positive joules per mole. So it was that case where if they're both positive, whether it's spontaneous or not, it's dependent on above or below the equilibrium temperature. But we can solve it, right? When delta G is 0, you rearrange, solve for T. It's delta H over delta S. You plug those numbers in, and magically you get 0 degrees Celsius. Well, it's in Kelvin, so 273 Kelvin. You can kind of see that on this graph here. Let me just, because the graph is on here, let's just talk about it a little bit. This line here, this green line, this horizontal line, this is your delta H. It's labeled right here. And essentially, delta H is going to stay constant through most conditions. And that's what we're assuming on this figure. It's not changing because the pressure is constant. And if you may remember, enthalpy is simply the change in the heat, the thermal heat at constant pressure. That's how enthalpy is defined, at constant pressure. So that's not changing. That's a flat line. And then the purple one here, that's our T delta S line. Here's our equilibrium temperature. Okay? So when we're below it, at some value, temperature below that line, right, the T delta S value here is lower than the delta H value. And since in this case, they're both positive values, right? This is a positive value, and this is a positive value. So plugging that into the master equation, because it's delta H minus T delta S. So this will not be spontaneous anywhere in this blue zone because this value is smaller in magnitude than this value, and it's delta H minus T delta S. Yeah, but if we now extend it to this part of the graph, now the T delta S value is greater than delta H, and so it's just a graphical way to visualize what I have written on top in green. Really, you don't really need to spend much more time on that unless you want to understand what that graph means. We'll take a look at it again in this next example. Here's another reaction. Here's the rust reaction. Once again, and now we'll look at the values. Now delta H is negative and delta S is negative. So once again, if we plug this in, delta G is equal to delta H minus T delta S. Right? This is a negative value, and this is a negative value. So now for this reaction to be spontaneous, delta G needs to be less than 0. It needs to be negative. So you can see at low temperatures, right, because this is a negative times a negative, that's a positive value, right? So at low temperatures, this absolute magnitude has to be less than delta H for this to still be a negative number. If the T delta S value, given that entropy is decreasing, if this gets larger than that, then it's going to be a positive value and it's no longer spontaneous. And again, we can calculate what temperature. So look, here's the graph, all right? But now it's the reverse of what we just showed. So here's the equilibrium temperature. This is where delta G is equal to 0. When delta G is equal to 0, that means this is delta H is equal to T delta S, and we can solve for T. T is equal to delta H over delta S. But what temperature is it? Why don't you go ahead and calculate it? What's the equilibrium temperature for this rust reaction? Ah, yes. Classic mistake. No one's confident about the answer. All right, look. We've got delta G equals delta H minus T delta S. If we're at equilibrium, what do we know about these three values, any of them? Do you know anything about any of those three thermodynamic values when we're at equilibrium? Delta G is 0, that's right. So when delta G is 0, here, let's just do this formally. So now 0 is equal to delta H minus T delta S. And remember, these are all of the system. I'm just not writing that down each time. So now I can rearrange this. Delta H is equal to positive T delta S. And that equilibrium temperature is equal to delta H divided by delta S. This is at equilibrium. It's going to be this temperature right here on this graph. It's going to be that temperature where above it or below it, it's going to switch from being spontaneous to non-spontaneous, just like we showed with the ice example. So now we just plug it in. What's delta H? It's right here. Delta H is negative 1648 kilojoules per mole. What's delta S? It's right here. Negative 549.4 joules per mole Kelvin. Okay? So what is that? What does that give you? Gives you 3? What 3 what? It's about 3. That's true. What is it when you actually do the math?
9.
What do you get?
I thought you had to convert them.
Say that louder. Say that louder.
You're right.
Converting it from kilojoules to joules.
That's right. That's right. All right, that's the big mistake, okay? Oh, yeah. Because look, the units don't all cancel out. Mole cancels with mole, and nothing cancels with Kelvin, so we're going to end up with Kelvin in the numerator, if you can see that. But joules does not cancel with kilojoules, so we need to do a conversion. All right? And it doesn't matter which way you go as long as you're consistent, so I'll just erase this, and I'll just do the conversion in my head. We'll go to kilojoules, so this will be negative 0.5494 kilojoules per mole Kelvin. All right? It's a classic mistake that students make. Don't be that student. And it's because of the way that the convention of the units. I'm sure that the convention for entropy being in joules and not kilojoules is not just to mess students up. It's probably because those values are more in a range where you don't have to use as much ink on your quill point when you're writing all this down back in use as much ink on your quill point when you're writing all this down back in Isaac Newton's time or whenever this stuff was. It wasn't Isaac Newton. Entropy was Clausius, so it was a little bit later than that. So now we can do the calculation. What do we get?
About 3,000.
3 what?
3,000.
3,000 what?
No.
Oh, so you guys are doing some pretty big rounding here. Let's put some.
2,999.
Thank you. 2,999 Kelvin.
636.
Okay. And then if we want that in Celsius, right? We got to subtract 273 from that. We still get a pretty large number. 272 or 2,700, whatever, degrees Celsius. I'm not worried about sig figs here, okay? We can make this calculation, but this reaction, rust, will be spontaneous, what, above or below this temperature? Rust occurs spontaneously, what, above or below 2,700 degrees Celsius? Below. And, you know, the last time I checked, 2,700 Celsius is pretty hot, which means that pretty much this reaction will, in our daily lives, this reaction is always spontaneous. All right. So I promised you a little bit more math today, so I saved this doozy for the end, but it's really not that bad. This has all to do with the fact that these thermodynamic functions are all state functions. Now, who remembers what a state function is? Nobody wants to give it a try? The route you took to get to university today, is it always the same route that you take? You leave you leave your bed, okay? So bed, you're at equilibrium when you're asleep at bed. I mean, you're not dead, but let's pretend you're at an equilibrium state in bed. And then you come here and you sit in this chair, all right, in front of me, and you're at another equilibrium state. How you get from your bed to this chair, you've got all sorts of different ways to do that. You might stop off at Dunkin' on the way, right? Or if it's me, it'll be Starbucks, but that's okay. All right? But eventually you get to the same state. The states we're talking about are equilibrium states. The example that I like to show in class a lot is the mountain, right? And if you take the tram from state A to state B, so A is at the base and B is at the summit, right? You can take the tram straight up to B, or you can take the path that winds around and switchbacks, and sometimes it goes down and sometimes it goes back up, and finally makes it to B. And it might take you longer to do that, okay? But overall, if we're saying, like, let's say the altitude gained, or the potential energy gained, or any of that stuff, the delta is always the same, no matter the path that you took to get there. The delta, the difference in state 1 versus state 2 is always the same. And it says state, but this is really, these are equilibrium states. Okay? And a state function is just that. It's independent of the path taken to get there. And the beauty of all of these state functions is that you can do a series of calculations that collectively describe the difference between state A and state B, even if that's not exactly what you did. The perfect example of this is what you did when you looked at Hess's law. Everyone remember Hess's law? Hopefully, Hess's law?
I didn't.
Also called the summation of enthalpies. And we did a lab on that as well, right? We had a reaction that reaction itself we couldn't measure the enthalpy of, but there were a series, 2 or 3 reactions that if you did them each separately, and if you added up those 3 reactions like they were linear equations, they would all add up to the master equation that you're trying to get the enthalpy of. And you can measure the enthalpy on the individual ones. So if they all add up, if they all get you to the same place, and you can make those individual measurements, then you know what the enthalpy change was of the master reaction, even though you couldn't measure it directly. This equation is just a fancy way to show that using a special kind of enthalpy, the delta H of formation. Using formation reactions. Right? And the reason I saved this work till the end is because you can see here's a similar equation for delta S of reaction and delta G of reaction. Now it has the not symbol here, which means these are under standard conditions. All right. And remember, our standard conditions means that we can look these up in Appendix 4. That's that thermodynamic table, okay? So it's another way that we can actually calculate some of these values and then plug them into our master delta G equals delta H minus T delta S. You can also measure some of these in a calorimeter, all right? And in labs, sometimes it's fun to see how close you get to the actual values. But mechanically, right, the math here is simply taking the sum of, in this case, the delta G of formation, the standard delta G of formation, of all the products, and we subtract the reactants from that. All right? And the convention, we always do products minus reactants. The N, this is the moles, right? And this is the value of the thermodynamic quantity that we're measuring. And it's easiest really to show this to you by way of example, okay? Now that you know what these equations represent. So here's the equation for you, all right? But ultimately what we want to do here is calculate the value of delta S of reaction, okay, at 298 Kelvin, which is good because that's under our standard conditions, all right? That's what the knot is for too, right? So the values that we get, here's from the table. This is from Appendix 4. I just grabbed it for you. If you went to Appendix 4, you should find this same data here. Okay, so we're going to use those values. I'll show you how it works on this one, and then you'll get a chance to practice it a little bit, okay? So there's the equation up on top. We're going to calculate delta S, the standard change in entropy of the system. It's going to be equal to the sum of the standard molar entropies of the products. So we have to look. We've got carbon dioxide and H2, all right? And we have 1 mole of carbon dioxide and we have 3 moles of hydrogen gas. So that's where the N comes into play, all right? It looks like this. Let's do the products. We're going to have 1 mole. I'll just put everything out here for you. 1 mole of carbon dioxide. Carbon dioxide here you can see has a standard molar entropy of 213.8. That's joules per mole Kelvin. Okay, so again, this is moles, and this is CO2. We're going to add to that 3 moles of the standard molar entropy for hydrogen gas, which is 130.6 per mole, and we have 3 moles of that. Okay, so this is 3 moles of H2, and that's all of the products. And we now subtract from that the same thing from the reactant side. So we have 1 mole of methanol, that's CH3OH, and each mole is has an entropy of 239.9 plus 1 mole of the standard molar enthalpy of water. So that's 188.8. And that's your answer. You can see why I saved this till the end. It's just a bunch of number crunching. But it's a way for you to calculate this information from standard molar entropies. And you got to remember where this comes from. I told you where this came from. This data in Appendix 4 comes from the third law of thermodynamics, where at absolute zero, it's a perfect crystal and the entropy is 0. Comes from the third law. According to the textbook's description, by making careful measurements as you raise the temperature, as you change the temperature, you can calculate what the standard molar entropies are at 25 degrees Celsius. This is the data that I told you would always be a positive value because it comes from entropy is 0 at absolute 0. S equals 0 at 0 Kelvin. So it's always a positive value, and I told you that you might see it as a negative value in Appendix 4 if it's an ion, because the ion isn't actually solvated in the aqueous solution, it's just given it to you as an ion. I'm trying to avoid those examples so that you only have to look at this as a positive number. All right, so then you just crunch it in. I don't know, should we do it? Just to make sure you know how to use your calculator the right way? No, we don't need to. I'll just tell you the answer that I got, okay? And make sure you get the same answer. I got positive 176.9 joules per Kelvin. Now take a look at this reaction though. Do you expect entropy to be positive or negative if you just look at this reaction? Positive or negative, and why?
More moles of gas in the product.
Say it louder. We expect delta S to be positive because we've got 4 moles of gas in the products versus only 2 moles of gas in the reactants. Okay? So you should know how to number crunch, okay? You have to know how to just use your brain and look at a reaction and be able to tell, do I expect this value to be positive or negative? You should be able to do both things. All right? So that's the number crunching part of it. We can do the same thing with, here, let's jump to this example. This example is extreme, okay? It's making you do that calculation both for delta S, delta H, and delta G. And you can do it now, okay? Here, let's do this first. Look at the reaction. What do we expect the sign on delta S to be without doing any calculations?
Negative.
Well, you're asking me, I can tell in the tone you're asking me, is it negative? It's negative.
4 moles of gas.
4 moles of gas on the reactant side and only 2 moles of gas on the product side. So as written, going from the left side to the right side, as this arrow is implying, that's what I mean by as written. And if we're just based on the entropy alone, we wouldn't expect that reaction to be spontaneous. Of course, we don't know what the enthalpy is yet. We got to calculate that. So we don't yet know if it's spontaneous or not. We got to calculate delta H, and then maybe we'll need to calculate delta G because it might be one of these things where it's dependent on the temperature. Here's all the data in Appendix 4. So why don't you go ahead and why don't you calculate what delta H is going to be?
I don't know which numbers to use.
Okay, so we have 2 negative 92s. That's good.
I did it backwards.
You did it backwards, so now yours is negative? Okay, so we have 3 negative 92s, and I got negative 92.22.
We use the aqueous in the gas.
Exactly, right, and which is why I put this on here. So you need to practice extracting this stuff from the table. You've got to pay attention to the number of moles in the balanced equation because that's going to go here, okay? And now we need the value. We need delta H for the ammonia, but ammonia what? Ammonia is here and ammonia is here. You need ammonia in the gas phase. There is a difference because this is enthalpy. And you might imagine that there's some heat involved with ammonia going from the liquid phase to the gas phase. That's why there's 2 different values. We need this value, negative 46.1. Plus nothing, that's it. That's all we have for the products. And so from that we subtract what we have for the reactants, and so 1 mole of N2. Remember that the standard enthalpies of compounds as they're found in nature, or elements as they're found in nature, they've already formed. Remember, this is the delta H of formation value that we're using here. That's what this F. There's a little F here, see? This is formation. And if it's already formed, because it's in nature, then the value is 0. So that actually makes this calculation quite easy, because this is times 0 plus 3 times 0. But this whole thing just cancels out. So we have basically negative 92.2. That's kilojoules per mole. Okay, so now we have delta H. If we did delta S, I'll just do it for you real quick, okay? Delta S of the reaction, that's going to be, now we need those same values. We need for the S column, all right, we need this value, and this value. So that's going to look like this. It's going to be 2 times 192.5 minus 1 times, now we need 191.5 plus 3 times 130.6. right? And you add all that up, and you should get, you can check me later when you go home, I got negative 198.3. Now that's joules per Kelvin. Those are the units, all right, for entropy. It's really joules per mole Kelvin. Sorry. And we can do the same thing for delta G. Here's the delta G column, delta G of formation. We need this value, and this value. Just like we had for enthalpy, we've got some zeros in there, so it makes the calculation actually really easy. Delta G standard of the reaction is going to be 2 times negative 16.5 minus, and all this is going to be 0 for the same reason that it was for enthalpy. So that's going to be equal to negative, what is that, 33, right? 33.0, that's kilojoules per mole. And that's all that this question is really designed to do, to have you practice doing that calculation. But let me also show you now, remember, we've got our master equation, delta G equals delta H minus T delta S. And we're told that this is at 25 degrees, we're at 298 Kelvin. So we should be able to plug all these values in that we calculated from Appendix 4, and it should satisfy this equation as well, right? Let's see if it does. So delta H, so delta G is equal to delta H, which was minus 92.2, minus T, which is 298, delta S is 198.3, but that's joules. We need to convert that into kilojoules, okay? Negative 0.1983 kilojoules per mole Kelvin. This is Kelvin. This is kilojoules per mole. Does it equal 33? Okay, so good. Whoops, negative 33. So that's a check plus. Yes, it does. No, everything doesn't cancel out. I was being kind of sloppy, but yes, the units do. Let me. Units do cancel. Let me clean this up a little bit. There. So we've got Kelvin cancels with Kelvin, and everything is now in kilojoules per mole. So this is now the units of kilojoules per mole, which is good because that's the units of delta G. Glad you asked, because units are important. All right, let's do a few more fun calculations here. I think I skipped one up here. I think we pretty much just did this one. So why don't you guys go ahead and do it? What's the value of delta G? That's your target at 298 K. You're given the delta H of the reaction, and you're given the delta S of the reaction. What'd you get? Who else got negative 70.5 something? Good. Because you didn't make the mistake, right? The mistake is to not convert the joules to kilojoules or kilojoules to joules, but you might as well convert everything to kilojoules because the convention is that the units of delta G is kilojoules per mole. So I left this one blank, but just for your notes, this is negative 0.1465 kilojoules per mole Kelvin. And just as before, all the units cancel out, so Kelvin cancels, well, not all the units, but we're left with kilojoules per mole, and we get negative 70.5 kilojoules per mole. So you've all learned about ATP, right? And how ATP is the currency of the cell, right? But it's not, right? It's not like money that you can take to the bank and cash it in. And, hey, here's some energy. I'm going to go use it for my biochemical processes. It's all about delta G, and it's all about thermodynamic coupling of reactions. So here's a reaction up on top. Have you all learned glycolysis yet? All right, so the first step of glycolysis is you take glucose and you stick a phosphate on the 6-sugar to give you glucose 6-phosphate. Here's the reaction. There's ATP and there's glucose. This is the full reaction. But if you look at the thermodynamics of it, and now we're studying the thermodynamics of it. So look at each reaction individually. here's the ATP. Actually, let's look at this reaction here for the glucose 6-phosphate. If we just focused in on this reaction, glucose plus the phosphate goes to glucose 6-phosphate plus water. Is it spontaneous or is it non-spontaneous? It's non-spontaneous. And how do you know? Delta G is positive. So how does this reaction by itself happen? There's a separate reaction, ATP. Okay? ATP, when it gets hydrolyzed into inorganic phosphate plus ADP, that reaction is thermodynamically favorable. It's spontaneous. Why do you suppose that one's spontaneous?
Delta G is negative.
Because what? Besides because delta G is negative. Look at the reaction. Why do you think that one's negative? It's hard to tell, I guess, because you've got 2 molecules, 2 moles of reactants, and you have 2 moles of products. So maybe that's a hard one to answer. It's what?
The phosphate group was divided.
Is divided. So you had, right, so think about this. It's not necessarily shown on here easily, okay? But you've got a negative charge here. You've got 4 negative charges on ATP. Here you've got 1, 2, 3 negative charges, and you got more negative charges here, but look at what you're doing. You're separating them. Negatives don't like being close to each other because same charges repel. So in ATP, you've actually got 4 negative charges all bound up close to each other because they're covalently bonded in the same molecule. Whereas if you split them, you're separating the charge. There's several things that are going on here. Another thing is if you take a look at the phosphate polyatomic ion, you may remember this from Gen Chem 1. This is the Lewis structure of the phosphate ion with 3 minus charges. But really, you don't have 1 double bond and 3 single bonds. You've got that double bond is in resonance over the whole molecule. So we can draw 4 resonance structures to describe phosphate. Or if you learned anything about hybrid orbitals like sp2, sp3, did you learn that? Right? It's distributed, right? The whole point here is that these electrons, the valence electrons, are in resonance. And when electrons are in resonance, that means that they're really spread more evenly across the whole molecule rather than just being right there on a particular atom or in a bond. And the more you can spread out your charge of the same magnitude, the more stable you are. But this is why ATP is so valuable, because when it hydrolyzes, right, you have greater stability in these products, all right? So that gives you a negative delta G. But if we coupled these reactions together, treated them as a series, right, even though they're happening separately, we consider them in a series, then together, overall, we just add them up. And we find that overall, it's minus 16.7 kilojoules per mole. So the coupled reaction is spontaneous, even though the important reaction here, getting glucose phosphorylated, is non-spontaneous. And that's all that question was asking about. You just figure out how you add them up to get to the third equation, and then you add up the delta G's. Okay, so the one on top is what you're trying to describe, and you're given these 2 equations. How can you manipulate reaction 1 and reaction 2 to give you this top reaction? Well, we don't need to do anything to reaction 1 because we have A and 2B in the products, in the reactant side. And what we need is 2C and 2D in the products, but we got 4C here, but we got 1C here. So let's see. Are you sure this is what it said?
Multiplied by 2.
Yeah. Oh yeah. So if we take reaction 2 and we multiply it by we need 2D. So if we multiply it by 2, take this 1 times 2, we're going to have 2C goes to 2D, right? And if I now add that to A plus 2B goes to 4C, what do we have? Because 2C cancels with 4C, that gives us 2C here plus 2D, and then we have our A plus 2B. So they add up this way. So if I do the same thing with the delta G's, let's see. So the one that I multiplied by 2, so that would be minus 860. And this one is 374. So that should be your answer. What is that?
486.
486. Negative. Is that the right answer? There you go. Ta-da!